What if I told you that everything you've ever been taught about the size of the universe is laughably, almost insultingly wrong? Not just a little off, but so fundamentally incorrect that when you see what the James Webb Space Telescope has revealed, your brain will physically struggle to process it. Right now, at this very moment, you're moving through space at 1.3 million miles per hour. You're not sitting still. You never have been. And the destination? There isn't one. Because the universe isn't just big. It's not even incomprehensibly large. It's something far more disturbing than that. 3 months ago, the James Webb Space Telescope pointed its instruments at what astronomers call the deep field, a patch of sky so small it would be covered by a grain of sand held at arm's length. What it found there shattered every calculation we had about cosmic scale. In that tiny speck of nothing, Webb detected 45,000 galaxies. Not stars, galaxies, each containing hundreds of billions of stars. But here's where it gets genuinely frightening. Some of those galaxies are so far away that we're seeing them as they existed just 300 million years after the Big Bang, a time when they theoretically shouldn't exist according to our models. They're too big, too organized, too mature. It's like finding a full-grown oak tree in the maternity ward. Dr. Jane Rigby, Webb's project scientist at NASA, said something in her August 2023 briefing that should have made headlines everywhere. We're going to have to rewrite the textbooks. The universe at its earliest moments was far more complex than we ever imagined. What she didn't say, but what the data screams, is that our entire cosmic timeline might be wrong. And if the timeline is wrong, then our understanding of scale, of distance, of everything out there collapses like a house of cards. But before we dive into what Webb revealed, I need you to understand something crucial. Your brain is actively lying to you about scale right now. Evolution designed your mind to understand the distance between you and a predator, between you and food, between your tribe and the next valley over. It did not prepare you for light years, for cosmic voids, or for the fact that the observable universe might be an infinitesimally small bubble in something unimaginably larger. By the end of this journey, you won't just know about the scale of the universe. You'll feel it in a way that might actually change how you see everything around you. Fair warning, some people find this existentially terrifying. Others find it liberating. No one finds it comfortable. Before we go further, if you want to join me on this mind-bending journey through cosmic scale, hit that subscribe button. And I'm genuinely curious. Drop a comment telling me where in the world you're watching from and what time it is for you right now. Because while we're scattered across this tiny planet, we're about to explore something that makes our differences seem beautifully, almost comically irrelevant. Let's start with something you think you understand. How far away is the moon? Most people would say, pretty far. Some might know it's roughly 240,000 miles away. That sounds like a lot, right? But let me give you a sense of scale that your brain can actually process. If you could drive to the moon at highway speeds, 65 miles per hour, never stopping for gas or sleep, it would take you 154 days. About 5 months of continuous driving. That's just to reach something we can see with our naked eyes every night. Now, the sun is much farther, about 93 million miles away. Using that same car, it would take 163 years of non-stop driving. You'd start the journey as a young adult, and your great-great-grandchildren would arrive at the sun. But here's where your brain starts to break. Neptune, the furthest planet in our solar system, is 2.8 billion miles away. That same car journey? 4,900 years. That's longer than recorded human history. The Egyptians hadn't built the pyramids when you'd need to have started driving to arrive at Neptune today. And Neptune, as distant as it seems, is in our cosmic backyard. It's so close that in the scale of the universe, the distance to Neptune is effectively zero. Not metaphorically zero. Functionally, mathematically, cosmically zero. Think of it like this. If the sun were the size of a period at the end of this sentence, Earth would be a speck of dust about an inch away. Neptune would be about 2 feet away. And the nearest star system, Alpha Centauri, it would be 4 miles away. 4 miles of emptiness containing that one period and a few dust specks. Dr. Neil deGrasse Tyson once calculated something remarkable. If you represented every meter of distance to the nearest star as a single second of time, it would take 135 years just to count to Alpha Centauri. And that's our nearest neighbor. The star you see next to it in the night sky might be thousands of times farther away, but they look the same to us. Your eyes are lying about distance constantly. This is where we need to abandon miles and kilometers. They're cute units for terrestrial distances, but in space, they become meaningless. From here on, we measure distance in light years. The distance light travels in 1 year. And light is fast, ridiculously fast. It travels 186,282 miles every single second. In 1 year, light covers about 5.88 trillion miles. Alpha Centauri, our nearest stellar neighbor, 4.37 light years away. That means when you look at Alpha Centauri tonight, you're seeing light that left that star 4.37 years ago. You're literally looking into the past. That's not a metaphor. The star could have exploded 2 years ago, and you wouldn't know for another 2 years. But here's something that should make you deeply uncomfortable. We have no way of knowing what's happening now anywhere else in the universe. The concept of now breaks down across cosmic distances. When you look at the moon, you see it as it was 1.3 seconds ago. The sun, 8 minutes ago. The center of our galaxy, 26,000 years ago. Now doesn't exist in space. There is only then. In 1995, astronomer Bob Williams made a controversial decision that many called a waste of precious telescope time. He pointed the Hubble Space Telescope at an empty patch of sky near the Big Dipper for 10 consecutive days. Not at a known star or galaxy, just at darkness. People thought he was crazy. That's 150 hours of Hubble time, time that astronomers compete desperately for, aimed at nothing. The image that came back, now called the Hubble Deep Field, revealed approximately 3,000 galaxies in that empty patch. Every fuzzy dot in the image wasn't a star, but an entire galaxy containing hundreds of billions of stars. In a patch of sky smaller than a grain of sand, held at arm's length. Suddenly, empty space wasn't empty at all. It was densely packed with galaxies we simply hadn't looked hard enough to see. Scientists did the math based on that image. If every patch of sky contained that many galaxies, then the observable universe must contain approximately 200 billion galaxies. That number stood for decades. 200 billion galaxies, each with hundreds of billions of stars. The numbers were already incomprehensible. But in 2016, using more advanced analysis techniques and deeper observations, Christopher Consuelos and his team at the University of Nottingham recalculated. They published their results in the Astrophysical Journal. The observable universe contains at least 2 trillion galaxies, not 200 billion, 2 trillion. They had been off by a factor of 10. Imagine if you thought your house was 2,000 square feet and then discovered it was actually 20,000 square feet. Except this is the entire universe we were wrong about. 2 trillion galaxies, each containing an average of 100 billion stars. That's 200 sextillion stars. Written out, 200 If you counted one star per second, it would take you 6.3 quadrillion years to count them all. The universe is only 13.8 billion years old. You'd need 457,000 universe lifetimes to finish counting. And here's the really disturbing part. That's just the observable universe. That's only the part of the universe where light has had time to reach us since the Big Bang. The actual universe? We have no idea how big it is. It might be infinite. It might curve back on itself. It might be part of an infinite multiverse. We literally don't know. Let me put this in perspective with something your brain can almost grasp. If you represented the entire observable universe as the Earth, our galaxy, the Milky Way containing 400 billion stars, would be about the size of a dust mite, not a coin, not a pebble, a microscopic dust mite. And our solar system? It would be invisible even under a microscope at that scale. And Earth? Earth wouldn't even be a single atom at that scale. It would be a fraction of the space inside an atom. Dr. Michelle Thaler, an astronomer at NASA's Goddard Space Flight Center, put it this way in her 2022 lecture. When students ask me what they should feel when they learn about cosmic scale, I tell them the only appropriate response is a kind of vertigo. Your brain should feel like it's falling, because in a very real sense, it is. Every assumption it evolved to make about space and scale is failing. But the James Webb Space Telescope has revealed something even more mind-bending. We've been measuring the scale all wrong. And when you understand why, everything you think you know about the universe's size will seem quaint and outdated. Are you ready to go deeper? Because what comes next will fundamentally change how you perceive distance, time, and reality itself. When the James Webb Space Telescope became operational in July 2022, astronomers weren't just excited about seeing farther. They were excited about seeing clearer. Webb doesn't observe visible light like Hubble. It observes infrared light, which might sound like a technical detail, but it changes everything about what we can see and how far we can see it. Here's why. Light stretches as it travels through expanding space. This is called redshift, and it's one of the most important concepts in modern astronomy. When a galaxy is moving away from us, its light gets stretched to longer, redder wavelengths. The farther away the galaxy, the more its light has been stretched, and the more extreme the redshift. The most distant objects have been stretched so much that their visible light has been shifted all the way into the infrared spectrum, invisible to telescopes like Hubble. Webb can see infrared light. That means it can see objects that have been literally stretched out of visibility for every other telescope we've ever built. It's not just a better telescope. It's seeing a part of the universe that was previously completely hidden from us. In Webb's first deep field image, released in July 2022, scientists identified a galaxy with a redshift value of Z equals 13.2. Let me translate that. This galaxy, called CERS 93316, existed approximately 235 million years after the Big Bang. We are seeing it as it was 13.6 billion years ago. The light that hit Webb's sensors has been traveling through space for 13.6 billion years. For context, Earth is only 4.5 billion years old. That light had been traveling for 9 billion years before our planet even existed. But here's where scale becomes truly bizarre. If that galaxy still exists today, where is it now? Not 13.6 billion light years away. Because space itself has been expanding the entire time that light was traveling toward us. Dr. Brant Robertson from UC Santa Cruz calculated that CER S93316 is now approximately 33 billion light years away from us. The light we're seeing left when the galaxy was 13.6 billion light years away. But in the time it took that light to reach us, the expansion of space has pushed the galaxy itself to 33 billion light years away. Read that again, because it's deeply weird. The light took 13.6 billion years to reach us, but the object that emitted the light is now 33 billion light years away. How is that possible? How can something be farther away than the age of the universe multiplied by the speed of light? Because space itself is expanding. Not just the things in space moving through space, but space itself growing like a balloon being inflated. And there's no speed limit on how fast space can expand. The speed of light is the cosmic speed limit for things moving through space, but space itself can expand faster than light. In fact, any galaxy more than about 14 billion light years away from us right now is receding from us faster than the speed of light because of the expansion of space between us. This means something profoundly disturbing. The observable universe has an edge, but it's not a real edge. It's a horizon beyond which light will never reach us, not because it's not trying, but because space is expanding too fast for the light to ever make progress toward us. Galaxies beyond that horizon are moving away from us faster than their light can travel toward us. They're running on a cosmic treadmill set faster than they can run. The edge of the observable universe is currently about 46.5 billion light years away in every direction. That makes the observable universe a sphere about 93 billion light years across. But remember, the universe is only 13.8 billion years old. How can we see something 46.5 billion light years away if light has only had 13.8 billion years to travel? Because that light left when space was much smaller and denser. The light has been traveling for 13.8 billion years, but space has been expanding the entire time, stretching the distance behind it. It's like if you started walking forward on one of those airport moving walkways, but the walkway was also stretching as you walked, making your starting point move farther and farther behind you, faster than you're walking forward. Astrophysicist Ethan Siegel describes it perfectly. The universe is like a loaf of raisin bread baking in an oven. As the bread expands, every raisin moves away from every other raisin. If you're a raisin looking out, every other raisin appears to be moving away from you. And the farther away a raisin is, the faster it's receding. But no raisin is moving through the bread. The bread itself is expanding. This is the metric expansion of space, predicted by Einstein's general relativity and confirmed by Edwin Hubble's observations in 1929. Hubble discovered that every galaxy we can see is moving away from us, and the farther away it is, the faster it's receding. This is called Hubble's law, and it gave us the Hubble constant, a number that describes how fast the universe is expanding. But here's where things get genuinely controversial, and where Webb has dropped a bomb on cosmology. Different ways of measuring the Hubble constant give different answers. And they shouldn't. This is called the Hubble tension, and it's one of the biggest crises in modern physics. When we measure the expansion rate by looking at distant supernova, we get one number, about 73 kilometers per second per megaparsec. When we measure it by looking at the cosmic microwave background radiation, the afterglow of the Big Bang, we get a different number, about 67 kilometers per second per megaparsec. These measurements should agree. They don't, and the discrepancy is too large to be experimental error. Dr. Adam Rees, who won the Nobel Prize for discovering that the universe's expansion is accelerating, has been leading the effort to resolve this tension. In April 2023, using data from Webb combined with Hubble observations, his team published results that confirmed the higher value with unprecedented precision. The universe, locally at least, is expanding faster than our models predict it should be. What does this mean? Honestly, we don't know. It might mean there's something wrong with our understanding of cosmic evolution. It might mean the universe is not uniform, that it's expanding at different rates in different regions. Or it might mean there's some unknown physics, some unseen force or particle that's affecting expansion in ways we don't understand. Some physicists half-jokingly call this unknown factor crisis cosmology. But for our understanding of scale, the implications are staggering. If the universe is expanding faster than we thought, then it's bigger than we calculated. The observable universe might not be 93 billion light years across. It might be larger. How much larger? We don't know. We don't even know if we're measuring the right things to find out. And here's something that will make you deeply uncomfortable. There are galaxies we can see right now that we will never be able to reach, even if we could travel at the speed of light. The expansion of space between us and them is so rapid that even a light-speed spacecraft would never close the distance. They're already gone from our universe in every practical sense. We can see their ancient light, but they've been carried beyond a horizon we can never cross. In fact, the situation is worse than that. Because the universe's expansion is accelerating, driven by something we call dark energy, more and more galaxies are crossing that horizon every day. The observable universe is getting smaller in terms of what we can eventually reach, even as we're seeing farther back in time. Billions of years from now, if humanity or some other intelligence is still around, they'll look out at the universe and see almost nothing. All the distant galaxies will have redshifted beyond visibility, accelerated beyond the cosmic horizon. The universe will appear dark, empty, and static, exactly as astronomers in the 1920s thought it was before Hubble's discoveries. Future astronomers will have no way of knowing the universe is expanding, no way of knowing there was a Big Bang, no way of knowing there are other galaxies beyond their own. All the evidence will have literally sailed over the cosmic horizon. If we hadn't happened to exist in this particular cosmic epoch, we might never have learned the truth about the universe's scale and history. Let me bring this back to something visceral. Right now, at this moment, light is hitting your eyes from galaxies that no longer exist in a form we could recognize. Light is hitting Webb sensors from galaxies that will have evolved, collided, been ripped apart, or gone completely dark billions of years ago. We're not seeing the universe as it is. We're seeing a museum of how it was, with the most distant exhibits showing us a universe that was young, small, and fundamentally different. The universe isn't just big. It's four-dimensional, with time and space inextricably mixed. Every direction you look in space is also a direction backward in time. And the James Webb Space Telescope has given us the ability to look farther back than ever before, which means we're seeing the universe when it was younger, smaller, and stranger than we ever imagined. But what Webb found when it looked back that far should not exist according to our theories. And that discovery is about to blow your mind in a way that might actually make you angry at how wrong we've been. When James Webb Space Telescope captured its first deep-field images in July 2022, astronomers expected to see faint, small, primitive galaxies. The early universe, just a few 100 million years after the Big Bang, should have been a chaotic mess. Baby galaxies, protogalactic clouds, nothing organized, nothing mature. Think of it like looking at Earth 100 million years after it formed. You'd expect molten rock, violent impacts, nothing resembling the organized planet we have today. That's not what Webb saw. Instead, it found massive, mature galaxies that shouldn't exist. Galaxies with clear spiral structures. Galaxies with hundreds of billions of stars already formed. Galaxies so large and so organized that they would have needed billions of years to develop, except they only had a few 100 million years at most. Dr. Ivo Laub from Swinburne University of Technology was part of the team analyzing Webb's first images. In February 2023, his team published a paper that sent shockwaves through the astronomical community. They had identified 6 massive galaxies, each with stellar masses comparable to the Milky Way, existing just 500 to 700 million years after the Big Bang. According to standard models of galaxy formation, these galaxies are impossibly early, as Dr. Laub phrased it. Here's why this is such a problem. Galaxies form through a process that takes time. First, you need dark matter to clump together under gravity, creating gravitational wells. Then normal matter, hydrogen and helium gas, falls into those wells. Then that gas needs to cool down enough to collapse and form stars. Then those stars live, die, and scatter heavier elements. Then new generations of stars form from that enriched gas. This is a slow process. It should take 1 billion years minimum to create a large, mature galaxy. But Webb is seeing mature galaxies at 500 million years. It's like expecting to find bacteria in a primordial soup and instead finding a fully formed dolphin. And numbers are staggering. These early galaxies are producing stars at rates 10 to 100 times faster than galaxies in the modern universe. They contain stars that have masses we rarely see today. And most disturbing, they exist in such high numbers that they account for way more mass than our models predict should exist at that time in cosmic history. Zhao Leia from Penn State, co-author of the study, said something that perfectly captures the crisis. We looked at the very early universe for the first time and had no idea what we were going to find. It turns out we found something so unexpected, it actually creates problems for science. It calls the whole picture of early galaxy formation into question. Think about what that means for scale. If galaxies formed faster than we thought, then the universe was more active, more productive, more organized at early times than we believed. Which means when we calculate the mass of the early universe, the number of stars that should exist at different epochs, the amount of time needed for cosmic structure to develop all of those calculations are wrong. We've been measuring cosmic scale with a ruler that's marked incorrectly. But it gets weirder. In September 2023, another team led by Jorrit Matthey at ETH Zurich discovered something even more problematic. They found supermassive black holes, billions of times the mass of our Sun, existing just 400 million years after the Big Bang. Supermassive black holes are theoretically formed through a process that's even slower than galaxy formation. First, massive stars form and die, creating stellar mass black holes. Then those black holes merge or accrete matter over vast periods, growing to thousands of solar masses. Then those intermediate mass black holes merge or accrete for even longer, eventually becoming supermassive. This process should take, conservatively, over 1 billion years. Webb is seeing the end result of this process at 400 million years. It's not just improbable. According to our standard models, it's impossible. Dr. Priyamvada Natarajan from Yale University, one of the world's leading experts on black hole formation, called these findings a complete surprise and admitted that we're going to need new physics to explain this. Our current theories simply don't allow for black holes this massive to exist this early. New physics. Let that sink in. When a scientist says we need new physics, they're not saying we got a detail wrong. They're saying our fundamental understanding of how the universe works is incomplete or incorrect. Here's one proposed solution that's both elegant and terrifying. What if the early universe was more violent and energetic than we imagined? What if the first stars weren't just massive, but supermassive, hundreds or thousands of times the mass of our Sun? These hypothetical population 3 stars would burn incredibly hot and die incredibly fast, potentially creating intermediate mass black holes directly, skipping the slow accumulation process. But here's the problem with that solution. We've never seen a population 3 star. They should be impossible to see because they existed so early that their light would be too faint and too redshifted. Except Webb can see that far back now. And it's not seeing population 3 stars. It's seeing mature galaxies that already have multiple generations of stars in them. The alternative explanations are even more radical. Some physicists are suggesting that our understanding of the Big Bang timeline itself might be wrong. What if the universe is older than 13.8 billion years? What if the Big Bang wasn't the beginning, but a transitional event in a much older cosmos? What if time itself behaved differently in the early universe, running faster in some quantum mechanical sense, allowing billions of years of evolution to happen in millions of years of clock time? These aren't fringe theories anymore. These are being published in peer-reviewed journals by respected institutions because the James Webb data is forcing us to consider them. Physicist Brian Greene, in a November 2023 lecture, put it this way: every time we build a more powerful telescope, we expect to confirm our theories with greater precision. Instead, Webb is doing the opposite. It's showing us that the universe at cosmic dawn was far stranger, far more complex, and far more active than our neat theories predicted. This is simultaneously thrilling and deeply unsettling. But let's zoom out from galaxies and black holes for a moment and talk about something even larger, the cosmic web itself. When you look at the distribution of galaxies in the universe, they're not spread randomly. They're organized into an enormous web-like structure, with galaxies clustered along filaments separated by vast cosmic voids. These filaments stretch for hundreds of millions of light years, containing thousands of galaxies strung like pearls on cosmic strings. Between them are voids, regions of space almost entirely empty of galaxies, some spanning over 1 billion light years across. The largest known structure in the universe is the Hercules Corona Borealis Great Wall, discovered in 2013. It's a galactic filament that spans approximately 10 billion light years across. 10 billion light years. That's more than 2/3 the distance to the edge of the observable universe. It's so large that light takes 10 billion years just to cross from one side to the other. But here's what's unsettling. Structures that large shouldn't exist according to the cosmological principle, which states that at the largest scales, the universe should be uniform and homogeneous. A 10 billion light-year structure violates that principle. It's too organized, too large, too lumpy for a universe that's supposed to be smooth at cosmic scales. And Webb has made this problem worse. By revealing that large galaxies existed much earlier than expected, it's suggesting that the cosmic web itself formed faster and more efficiently than our models predict. The universe has been organizing itself into large-scale structures more quickly and more thoroughly than we thought possible. Dr. Daniel Pomeride from Paris-Saclay University, who creates visualizations of cosmic structures, said in 2023, "We thought we understood how matter organized itself on cosmic scales. Webb is telling us we were naive. The universe has been busy doing complex things while we weren't watching. Now, let me give you a sense of scale that will make all of this feel viscerally real. Our galaxy, the Milky Way, is approximately 100,000 light years across. That seems enormous until you realize it's a single point in the cosmic web. The Milky Way is part of the Local Group, a small cluster of about 80 galaxies spanning about 10 million light years. Still feels big, right? The Local Group is part of the Virgo supercluster, a larger structure containing about 100,000 galaxies spanning 110 million light years. Now we're getting to scales where your brain starts to struggle. But the Virgo supercluster is just a small part of Laniakea, an even larger supercluster containing about 100,000 galaxies spanning 520 million light years. Laniakea was only discovered and mapped in 2014 by Brent Telly and his team. We live in it. We didn't even know it existed until a decade ago. And Laniakea is just one lobe of something even larger. It's connected to other superclusters in the cosmic web. We're a galaxy in a local group, in a supercluster complex, in a web that stretches across the entire observable universe. Now think about this. If you could somehow step outside the universe and look at it, the cosmic web would look biological. It would look like neurons in a brain, or like the mycelial network of fungi spreading through soil. The resemblance is so striking that some physicists have done statistical analyses comparing the large-scale structure of the universe to the structure of the human brain. The number of galaxies in the observable universe is roughly equal to the number of neurons in the human brain. The way they're connected shows similar network properties. No one knows if this means anything. It might be pure coincidence. Or it might hint at some deeper mathematical principle that governs how complex networks organize themselves, whether those networks are made of neurons or galaxies. But here's what James Webb has revealed that changes everything about this picture. The early universe didn't build this structure slowly and gently. It built it fast and violently. The cosmic web isn't a slow accumulation. It's the scar tissue of an incredibly dynamic, energetic young universe that was doing things we didn't think were possible. And that means when we look at the scale of cosmic structures, we're not looking at something stable and permanent. We're looking at a snapshot of an ongoing process that began more mysteriously and evolved more rapidly than we ever imagined. The scale of the universe isn't just about size anymore. It's about time, energy, complexity, and a history that we're only beginning to understand was far stranger than our theories predicted. Are you feeling that vertigo yet? That sense that the ground beneath you is less solid than you thought? Because we're about to go deeper into something that will make even galaxies and superclusters seem small. The question of what the universe is expanding into, and what might lie beyond our cosmic horizon. When people learn that the universe is expanding, they almost always ask the same question: what is it expanding into? It's such a natural, intuitive question. If something is getting bigger, it must be growing into a space that already exists, right? Wrong. And understanding why that's wrong is crucial to grasping the true scale of the universe. The universe isn't expanding into anything. Space itself is expanding. There's no outside of the universe that it's growing into. The balloon analogy I used earlier is imperfect because when you imagine a balloon inflating, you picture it expanding into the room around it. But the universe isn't a balloon in a room. It's more like the surface of the balloon is the only thing that exists, and that surface is stretching. There is no room around it. There is no beyond it. The universe is everything, and everything is expanding. This is one of the most counterintuitive concepts in all of physics, and even trained physicists sometimes struggle to internalize it fully. Your brain wants an edge. It wants a boundary. It wants to know what's past the fence. But the universe doesn't have a fence. It has a horizon, but that horizon is a limit on what we can see, not an edge to the universe itself. Think of it like being on a ship in the middle of the ocean. You can see to the horizon in every direction, and that creates a circle of visibility around you. But there's no edge to the ocean at that horizon. It's just the limit of how far you can see because of the Earth's curvature. The universe's horizon works similarly, except instead of being limited by the Earth's curvature, you're limited by the speed of light and the age of the universe. But here's where things get philosophically disturbing. What if the universe is infinite? What if there's no edge, because it simply goes on forever in all directions? Current observations suggest the universe is flat, or very close to flat. In cosmology, flat doesn't mean two-dimensional. It means that parallel lines will never converge or diverge, that the geometry of space follows Euclidean rules. And a flat universe that's also infinite is entirely consistent with our observations. In fact, according to measurements of the cosmic microwave background by the Planck satellite in 2018, if the universe is closed and finite, it must be at least 250 times larger than the observable universe. But it could also be infinite. If the universe is infinite, then something deeply weird is true. Everything that can happen will happen, an infinite number of times, somewhere out there beyond our horizon. Max Tegmark, a cosmologist at MIT, calculated in 2003 that in an infinite universe, the exact arrangement of particles that makes up you, your body, your memories, everything, must repeat. Because there are only so many ways particles can be arranged in any given volume of space. If space is infinite, then every possible arrangement must occur somewhere. And if it must occur somewhere, it must occur an infinite number of times in infinite space. This means that in an infinite universe, there is another you, reading this exact script, somewhere approximately 10 to the power of 1,029 meters away. That number is so large that writing it out normally would require more atoms than exist in the observable universe. But in infinite space, that unimaginable distance is trivial. There are infinite versions of you out there, some slightly different, making different choices, some identical, living parallel lives, some in universes that are completely different from ours. But wait, I said, in universes that are completely different from ours. That's not quite right. These aren't other universes. They're still our universe, just so far beyond our cosmic horizon that we can never see them, never interact with them, never know they exist. They're observationally equivalent to other universes, but they're technically just very, very cosmically distant parts of our own universe. Unless, of course, the multiverse is real. And this is where cosmology veers into territory that makes some physicists deeply uncomfortable and others genuinely excited. The idea of a multiverse comes in several flavors. The simplest version is what we just discussed. An infinite universe with infinite variations of everything, all existing within the same space-time. But there are more exotic possibilities. Inflationary cosmology, developed by Alan Guth in 1981 and refined by André Linde, André Albrecht, and Paul Steinhardt, suggests that the Big Bang was preceded by a period of exponential expansion called inflation. In a tiny fraction of a second, space expanded by a factor of at least 1026, growing from smaller than an atom to larger than a galaxy, in less time than it takes light to cross an atomic nucleus. Inflation solves several problems in cosmology, explaining why the universe is so uniform and flat. But it also creates a bizarre consequence. If inflation happened once, it's probably happening all the time, everywhere, eternally. In eternal inflation theory, our observable universe is just one bubble in an infinitely frothing foam of bubble universes, each created by inflation, and each potentially having different physical laws, different constants of nature, different numbers of dimensions. André Linde describes it like this: inflation is like a branching tree that perpetually grows new branches. Each branch is a universe. Our universe is just one leaf on one branch of an infinite tree. The tree as a whole never stops growing. These other bubble universes would be forever beyond our reach, separated from us by regions of space that are still inflating exponentially. They're not beyond our cosmic horizon in our universe. They're separate space-times entirely, causally disconnected from us. If the multiverse is real, then the scale of existence becomes literally infinite in a way that makes the observable universe seem like a single grain of sand on an infinite beach. Everything we've discussed so far, the 93 billion light-year span of the observable universe, the 2 trillion galaxies, the 200 sextillion stars, would be an infinitesimally small fraction of reality. But we have no way of confirming this. By definition, if other bubble universes are causally disconnected from us, we can't observe them. They make no predictions we can test. Some physicists argue this makes multiverse theory unscientific. Others argue that if inflation is correct, and inflation seems to be strongly supported by data, then eternal inflation and the multiverse are unavoidable consequences. We don't get to choose whether it's real based on whether we like the implications. Dr. Lisa Randall from Harvard has a nuanced take on this. The multiverse might be real, but we need to be very careful about making claims we can't test. That said, absence of evidence isn't evidence of absence. Just because we can't see other universes doesn't mean they don't exist. We need to follow the math and the physics wherever they lead, even if that's somewhere uncomfortable. Now, the James Webb Space Telescope can't see other universes or prove the multiverse exists. But it has revealed something about our universe that's made the multiverse theories seem more plausible. The universe at its earliest moments was already incredibly complex, already full of structure, already violating our expectations. It's as if the universe hit the ground running. And one explanation for that is that our universe didn't start from nothing. It budded off from something larger, some pre-existing structure in a multiverse. This is speculative. This is at the edge of science and metaphysics. But it's where the data and the theories are pushing us. Let me bring this back to something tangible. You are here, in this universe, reading this script. The fact that you exist, that conscious observers exist at all, is deeply strange. The constants of nature, the strength of gravity, the mass of the electron, the cosmological constant driving expansion, all of these are finely tuned to values that allow complex chemistry, stars, planets, and life to exist. If any of these constants were slightly different, the universe would be sterile. If gravity were slightly stronger, all stars would be so massive they'd burn out in millions of years, not enough time for life to evolve. If the electromagnetic force were slightly weaker, atoms wouldn't hold together. If the cosmological constant were slightly larger, the universe would have expanded so fast that galaxies could never form. This fine-tuning problem has puzzled physicists for decades. One solution is the anthropic principle. We observe these values because we can only exist in a universe with these values. It's survivorship bias on a cosmic scale. We're not in a special universe. We're in the only type of universe where observers like us could evolve to ask the question. But the anthropic principle only makes sense if there are many universes with different constants. If there's only one universe with one set of constants that happen to allow life, then the fine-tuning seems like a miracle. If there's a multiverse with infinite variations, then the fine-tuning is explained by probability. Somewhere in the infinite multiverse, every possible combination of constants exists, and we find ourselves in one of the rare regions where life is possible, because those are the only regions where anyone could find themselves. This is heavy stuff. This is the kind of cosmology that makes some people feel insignificant and others feel special. But what James Webb has done is make these questions more urgent, more immediate, by showing us that the universe's scale and complexity exceed our models at every turn. And there's something else Webb has revealed that we need to talk about, something that concerns the very fabric of space itself, and the largest mystery in modern physics: dark energy. Remember when I mentioned the universe's expansion is accelerating? That discovery, made in 1998 by two teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, won the Nobel Prize in 2011. They were studying distant supernova, explosions of stars that can be used as standard candles to measure cosmic distances. What they found shocked everyone. The most distant supernova were dimmer than expected, which meant they were farther away than they should be if the universe's expansion was slowing down due to gravity. The only explanation: the universe's expansion isn't slowing down, it's speeding up. Something is pushing space apart, overcoming the pull of gravity. We call that something dark energy, and it's the most abundant thing in the universe. About 68% of the universe's total energy content is dark energy. Another 27% is dark matter, the invisible stuff that holds galaxies together. And only 5% is normal matter, the stuff that makes up atoms, stars, planets, and you. We don't know what dark energy is. We have theories. It might be a property of space itself, a cosmological constant predicted by Einstein's equations. It might be a new field pervading space, something called quintessence. It might be a sign that our understanding of gravity breaks down at cosmic scales. We genuinely don't know. But what we do know is that dark energy is winning. The expansion of the universe is accelerating, which means galaxies are moving apart faster and faster. Eventually, in about 100 billion years, every galaxy beyond our local group will have receded beyond the cosmic horizon. The universe will appear dark, empty, and cold. But there's something even more disturbing that dark energy implies about scale. If the expansion continues to accelerate forever, then the ultimate fate of the universe is what's called the Big Rip. As expansion accelerates, it will eventually overcome not just the gravity holding galaxy clusters together, but the gravity holding galaxies together, then solar systems, then planets, then molecules, then atoms. Space itself will be torn apart at the seams, ripping reality into disconnected quantum pieces. The Big Rip is trillions of years in the future, so it's not something we need to worry about personally. But it fundamentally changes the meaning of cosmic scale. The universe isn't just big, it's temporary. All the structures we see, from galaxies to superclusters, are ephemeral patterns in space that will eventually be erased by expansion, unless dark energy changes. And this is where Webb comes back into the picture in a crucial way. By observing how the universe looked at different epochs, Webb is giving us data about how dark energy has behaved over cosmic history. Has it been constant? Has it been getting stronger? Weaker? Early results from Webb, combined with data from other sources, suggest that dark energy might not be constant. It might be evolving. And if it's evolving, then our predictions about the universe's fate might be completely wrong. The universe might not expand forever. It might eventually stop, reverse, and collapse back into a big crunch, or it might transition to some other state entirely that we haven't even imagined yet. Dr. Saul Perlmutter, in a 2024 interview, sighed, "Every time we think we understand the universe's scale and fate, new data throws us a curveball. Webb is the latest curveball machine. It's humbling and exhilarating at the same time. Now, let me step back and give you a sense of where we are in this journey. We started with the moon being 240,000 miles away. We moved to Neptune being billions of miles away. Then to the nearest star being 4.37 light-years away. Then to the observable universe being 93 billion light-years across. Then to the possibility of an infinite universe with infinite copies of you. Then to a potential multiverse of infinite universes. Then to dark energy accelerating expansion and potentially tearing everything apart. At each step, the scale has gotten larger, stranger, and more unsettling. But here's what I want you to feel right now. You're still here. You still exist. You're still a conscious observer, able to contemplate all of this. And that's not insignificant. In all of this vast, expanding, possibly infinite cosmos, consciousness is rare. As far as we know, it might be unique to Earth. It might be common. We don't know. But we do know that you are part of the universe that has become complex enough to understand itself. You're not separate from the cosmos. You're a piece of it, asking questions about the whole. Carl Sagan famously said, "We are a way for the cosmos to know itself." The James Webb Space Telescope is another way. It's an extension of human consciousness, built from atoms forged in stars, looking back at those stars and asking, how did we get here? How big is all of this? What does it mean? And the answer Webb is giving us is, it's bigger, older, stranger, and more wonderful than we dared imagine. And we're just getting started. But we're not done yet. There's one more layer to this that we need to explore. What does all of this mean for you, personally, in your daily life? How does cosmic scale change the way you see yourself and your place in existence? That's where we're going next. And I promise you, this is where everything we've discussed will click into place in a way that's both humbling and empowering. Let me ask you a personal question. When was the last time you felt truly small? Not small in a negative sense, but small in the context of something vast and beautiful? Standing at the edge of the ocean? Looking up at a night sky far from city lights? Visiting the Grand Canyon? There's a particular feeling that comes from confronting scale, a mixture of awe and insignificance that psychologists call the overview effect when astronauts experience it from space. But you don't need to go to space to feel it. You're feeling it right now, if you've been truly engaging with what we've discussed. Here's what I want you to understand about your place in all of this. You are small. That's not an insult. That's a fact. You are a temporary arrangement of atoms on a small planet orbiting an ordinary star in an unremarkable galaxy in a universe so large that your entire existence is barely a quantum fluctuation in cosmic terms. But here's the other truth. You are also vast. The atoms in your body were forged in the cores of stars that died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was created by nuclear fusion in stellar cores, or in the violent explosions of supernova. You are literally made of stardust. That's not a metaphor. That's chemistry. Lawrence Krauss, a theoretical physicist, calculated that every atom in your body has been part of approximately 1 billion different things before becoming part of you. The carbon atoms in your DNA were once part of a tree, before that an animal, before that plankton in an ancient ocean, before that carbon dioxide in the atmosphere of early Earth, before that gas in the molecular cloud that collapsed to form our solar system, before that material blown out by a dying star. You are ancient. You are recycled star matter. You are the universe experiencing itself subjectively. But let's go deeper. Your consciousness, your ability to read these words and contemplate your own existence, is the most complex thing we know of in the entire universe. Your brain contains approximately 86 billion neurons, each connected to thousands of others, creating trillions of synaptic connections. The number of possible states your brain can be in exceeds the number of atoms in the observable universe. Think about that. The complexity inside your skull exceeds the number of atoms in 93 billion light-years of space. Christoph Koch, a neuroscientist who studies consciousness, puts it this way: a single human brain, with its vast network of interconnected neurons, is capable of generating more possible thoughts than there are particles in the universe. In terms of informational complexity, you are larger than the cosmos. This is where scale inverts. Yes, you are physically tiny compared to galaxies and superclusters. But in terms of complexity, conscious structure, organized information, you are cosmically significant. A galaxy is big, but it's mostly empty space and simple hydrogen. It's not thinking, it's not experiencing, it's not aware of itself. You are. Now, let me connect this to something practical. In your daily life, you worry about things. You stress about your job, your relationships, your future, what other people think of you. These concerns feel enormous because they're immediate and personal, and they are important. Your life, your experiences, your relationships, these things matter deeply to you, and they should. But when you understand cosmic scale, something shifts. The things that seemed overwhelming start to feel more manageable, not because they don't matter, but because you gain perspective. The embarrassing thing you said last week, the mistake you made at work, the argument you had with a friend, these things feel universe-ending in the moment. But in the context of cosmic scale, they're tiny ripples in space-time, barely registering. This isn't about diminishing your problems. It's about right-sizing them, about seeing them clearly, about recognizing that you have the capacity to handle them because you're part of a universe that has been handling far more complex problems for 13.8 billion years. There's a meditation practice in some Buddhist traditions where you progressively zoom out from your immediate experience to larger and larger scales. You start by feeling your breath. Then you imagine zooming out to see your body, then your room, then your city, then your continent, then Earth, then the solar system, then the galaxy, then the universe. And then you zoom back in, returning to your breath with a sense of perspective. What we've done in this journey is a version of that practice. We've zoomed out to the largest scales we can measure or theorize about. And now I want to zoom back in, back to you, back to this moment, and ask, how does it feel different? For some people, contemplating cosmic scale leads to nihilism. If I'm so small and temporary, why does anything I do matter? It's a fair question, but I think it misses the point. Yes, you are small and temporary on cosmic scales, but so what? Meaning isn't derived from size or duration. A moment of genuine joy, a flash of insight, a connection with another person. These things don't need to be cosmic in scale to be meaningful. They're meaningful because you experience them, because they happen in consciousness, because they're real to you. The universe doesn't care about you. It's not malevolent. It's just indifferent. It's too large and simple to care. But that means you're free. You're not bound by some cosmic purpose or destiny. You get to create your own meaning. You get to decide what matters to you. And here's something beautiful. The things that tend to matter most to people, love, kindness, curiosity, creativity, growth, these things are amplified by cosmic perspective, not diminished. When you realize how unlikely your existence is, how rare consciousness might be, how precious the time you have is, it makes those moments of connection more valuable, not less. Carl Sagan, again, said it perfectly. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. And then he added, the significance of our lives. And our fragile planet is then determined only by our own wisdom and courage. You are a witness to the universe. You are part of the universe that has evolved the ability to understand, to question, to explore. The James Webb Space Telescope is an extension of that ability. Every image it captures, every galaxy it reveals, every mystery it uncovers, that's humanity reaching out into the cosmos, trying to understand our place in it. And you're part of that. By learning about cosmic scale, by grappling with these ideas, you're participating in one of the grandest intellectual endeavors in human history, the attempt to understand the universe we find ourselves in. But there's a practical dimension to this that I don't want to gloss over. Understanding cosmic scale changes how you see daily life in tangible ways. When you look up at the night sky, you'll never see it the same way again. Every star you see is ancient light. Some of those stars might not exist anymore. You're seeing the past. You're looking at a museum. And the vast darkness between the stars? That's not empty space. That's full of galaxies you can't see with your naked eye, each containing billions of stars, each hosting potentially billions of planets. The moon you see isn't just a pretty object in the sky. It's a world, tidally locked to Earth, moving away from us at 1.5 inches per year due to tidal forces. Billions of years from now, if Earth still exists, the moon will appear much smaller in the sky, and total solar eclipses will no longer be possible. We live in a narrow time window where the moon and sun appear almost exactly the same size from Earth, allowing perfect eclipses. That's not cosmic design. That's cosmic coincidence. The sun you see isn't just a light source. It's a nuclear furnace converting 4 million tons of matter into energy every second via fusion. It's been doing this for 4.6 billion years. It will continue for another 5 billion years. It's halfway through its life. When it dies, it will expand into a red giant, engulfing Mercury, Venus, and possibly Earth. Everything you know will be vaporized. But that's 5 billion years away. Life on Earth might have spread to other stars by then. Or we might be extinct. Either way, the universe will continue. The air you're breathing right now is 78% nitrogen, 21% oxygen, 1% other gases. That oxygen exists because of photosynthetic bacteria and plants that evolved to split water molecules and release oxygen as waste. For billions of years, Earth's atmosphere had almost no oxygen. If you went back in time to early Earth, you'd suffocate. The air you're breathing is a product of biological evolution, not a cosmic given. The ground beneath you is moving. Earth rotates at about 1,000 miles per hour at the equator. It orbits the sun at 67,000 miles per hour. The sun orbits the center of the Milky Way at 514,000 miles per hour. The Milky Way is moving toward the Andromeda Galaxy at 250,000 miles per hour. And the entire local group is moving toward the center of the Virgo supercluster at 1.3 million miles per hour. You are in constant, rapid motion. You just don't feel it, because everything around you is moving with you. Time itself is relative. Einstein showed this in 1905. Time moves slower in stronger gravitational fields and at higher speeds. GPS satellites have to account for time dilation because they're farther from Earth's gravitational field and moving fast relative to the surface. If they didn't correct for relativistic effects, your GPS would be off by miles within days. This means that time is moving slightly faster for you when you're in an airplane than when you're on the ground. You age microscopically faster at high altitudes. When astronauts return from the International Space Station, they've aged slightly less than people on Earth because they were moving fast and in a weaker gravitational field. These differences are tiny fractions of a second over months, but they're real and measurable. Space and time aren't fixed. They're flexible. They warp around mass. They stretch with expansion. They're part of a unified fabric called space-time that bends, flexes, and ripples. When you understand this, reality becomes both stranger and more wonderful. You're not living in a static universe with fixed laws. You're living in a dynamic, evolving cosmos that's been unfolding for 13.8 billion years and will continue to unfold for trillions more. And you're here, now, in this brief window of cosmic history, able to understand all of this. That's extraordinary. Let me give you one more gift of perspective. Right now, somewhere in the universe, light is leaving a distant galaxy, beginning a journey that will take billions of years. In the unimaginably distant future, long after our sun has died, long after the Milky Way has collided with Andromeda and formed a new galaxy, long after humanity is gone or evolved into something unrecognizable, that light will finally arrive somewhere. Maybe it will hit a telescope built by some future intelligence. Maybe it will just pass through empty space. But it's traveling now, carrying information about a moment in cosmic history. And in the same way, light is leaving your body right now, reflected or emitted, radiating out into space at the speed of light. In millions of years, that light will reach distant stars. It's a tiny amount of light, barely distinguishable from background radiation, but it's real. You are sending information about your existence out into the cosmos. You are, in a literal sense, becoming part of the universe's story, written in light. This is what James Webb Space Telescope has revealed about scale. It's not just that the universe is big. It's that the universe is interconnected, that everything affects everything else, that you are part of a vast cosmic ecosystem that's been evolving for eons and will continue to evolve long after you're gone. But while you're here, you get to experience it. You get to learn about it. You get to share it with others. You get to add your small but real contribution to the universe's complexity. And that, to me, is what makes cosmic scale not depressing but empowering. You're not insignificant. You're different. You're a unique configuration of atoms that exists for a brief moment, able to think, feel, and wonder. And that's enough. That's more than enough. That's everything. So the next time you feel overwhelmed by your problems, look up at the sky. Remember that you're on a planet orbiting a star in a galaxy that's part of a supercluster in an expanding universe that might be part of an infinite multiverse. Remember that the atoms in your body are ancient, recycled star matter. Remember that the consciousness in your head is the most complex thing we know of. And then come back to yourself, to this moment, to this life, and live it fully. Because you're not separate from the cosmos. You're an expression of it. You're a way for the universe to experience itself. And that's as meaningful as anything can be. Now, there's one final piece we need to discuss. Something that brings all of this full circle and connects James Webb's discoveries to the deepest questions humans have ever asked. Are we alone? In a universe this vast, with 2 trillion galaxies and 200 sextillion stars, with billions of years of cosmic history, with the mind-boggling scale we've explored, are we the only conscious observers? Or is the universe teeming with life, with intelligence, with other civilizations asking the same questions we are? This is the question that haunts every astronomer who looks at Webb's images. Because every galaxy, every star, every planetary system Webb reveals is a potential home for life. And the sheer number of possibilities makes the idea that we're alone seem almost absurd. But if we're not alone, where is everybody? That's the Fermi paradox, named after physicist Enrico Fermi, who asked it in 1950. If life is common, If intelligence arises often, if technological civilizations exist throughout the galaxy, why haven't we seen any evidence of them? Why hasn't anyone visited us or sent us a message? Why is the universe so quiet? There are many proposed solutions to the Fermi paradox. Maybe life is common, but intelligence is rare. Maybe intelligence is common, but technological civilization is short-lived. Maybe civilizations destroy themselves before they can spread to the stars. Maybe they're there, but hiding. Maybe they're there, but so different from us that we don't recognize their signals. Maybe we're early, the first intelligent civilization in our galaxy. Maybe space is just too vast, the distance is too great for civilizations to ever meet. Each of these solutions has implications for cosmic scale. If civilizations are short-lived, if they typically destroy themselves within centuries of developing technology, then the universe's vast scale becomes a quarantine mechanism. Civilizations rise and fall on isolated planets, never making contact because the timing never aligns. We could be in a galaxy full of ruins, planets where civilizations flourished briefly and then disappeared, leaving no lasting trace. If civilizations are long-lived, but space is too vast to cross, then the universe's scale is a prison. We're islands in an ocean too wide to navigate. We can see other islands on the horizon, but we can never reach them. We're cosmically alone, not because we're the only ones, but because the universe is too big for anyone to meet anyone else. Dr. Jill Tarter, who led the SETI Institute for decades, searching for signals from extraterrestrial intelligence, has a perspective that's both sobering and inspiring. The universe is big, really big, and we've only just started looking. We've searched maybe a swimming pool's worth of water in all the oceans on Earth. Just because we haven't found anything yet doesn't mean there's nothing to find. It means we need to keep looking. James Webb Space Telescope has already started finding potential biosignatures on exoplanets, planets orbiting other stars. In September 2023, Webb detected potential signs of dimethyl sulfide in the atmosphere of exoplanet K218b, a molecule that on Earth is only produced by life. It's not proof. It could be a false positive, but it's tantalizing. It's the first hint that we might, in our lifetimes, find evidence of life beyond Earth. And if we do, everything changes. If we find even simple microbial life on another planet, it means life is probably common. Because if it happened twice in one small corner of one galaxy, it's probably happening everywhere. The universe would go from being a vast, empty desert to a garden full of oases we just haven't visited yet. Or we might find evidence of past civilizations, structures on distant planets, megastructures around stars, signatures of industrial activity in exoplanet atmospheres. We might find that we're not the first, just the latest in a long line of civilizations that arose, flourished, and faded. Or we might find nothing. We might search for centuries and find that life, especially intelligent life, is so rare that we are effectively alone in the observable universe. We might be it, the only eyes looking out at the cosmos, the only consciousness asking these questions. And you know what? That would make us even more significant. If consciousness is rare, if we're one of the few or only places where the universe has become aware of itself, then we're precious beyond measure. We're not just observers. We're custodians. We're responsible for preserving and spreading consciousness, for ensuring that at least one part of the universe continues to understand itself. Dr. Carl Sagan, in his book Pale Blue Dot, wrote about a photograph taken by Voyager 1 in 1990, showing Earth as a tiny speck in a beam of sunlight, taken from 3.7 billion miles away. He wrote, "Look again at that dot. That's here. That's home. That's us. On it everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, Every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. That perspective, that understanding of scale, that's what Webb is giving us again, but deeper. Because now we're not just seeing Earth as a pale blue dot. We're seeing the observable universe as a bubble in possibly infinite space. We're seeing galaxies that existed when the universe was young. We're seeing the cosmic web. We're seeing the deep history of everything. And in all of that vastness, in all of that deep time, in all of those trillions of galaxies, you are here. You exist. You are conscious. You are thinking about all of this. And that's not nothing. That's everything. Let me end with this. The universe doesn't need you. It was here for billions of years before you were born. It will be here for trillions of years after you die. It's indifferent to your existence. But you need the universe. You're made of it. You're shaped by it. You're a brief, localized increase in complexity and consciousness in a cosmosly simple and unconscious. You're rare. You're temporary. You're precious. And now you know the true scale of it all. You know that the universe is bigger than we ever imagined, stranger than our theories predicted, more dynamic and complex than our models captured. You know that James Webb Space Telescope has shown us galaxies that shouldn't exist, structures that form too fast, a cosmic history that's more complicated than we thought. You know that you're made of star stuff, that your atoms are ancient, that your consciousness is cosmically significant, that your existence is improbable and brief and meaningful. So what do you do with this knowledge? You live, you love, you learn, you create, you connect with others. You add your unique perspective to the universe's ongoing story. You don't waste time on things that don't matter. You focus on what does. You remember that you're part of something vast and beautiful and strange. And maybe, on a clear night, you look up at the stars and feel that vertigo again, that sense of scale, that mixture of insignificance and significance. And you smile, because you understand. You're a temporary arrangement of atoms that can contemplate infinity. And that's as close to magic as the universe gets. Thank you for taking this journey with me. If this changed how you see the universe, even a little bit, hit that like button and subscribe for more mind-expanding content. And seriously, drop a comment telling me where you are and what time it is. Because while we're scattered across this tiny planet, we're all sharing this moment of cosmic understanding together. And that's beautiful. The universe is vast. You are small. And somehow, impossibly, it makes you matter more, not less. Keep looking up.